Let us solve few more numericals on parallel operation and on different connections of three-phase transformer. So numerical is given two single-phase transformers A and B in parallel are supplying a common load of 1000 kVA at 0.8 power factor lagging. The transformer A is 750 kVA and has ohmic drop of 3% and inductive drop of 5% at full load. Transformer B is of 500 kVA and has ohmic drop of 2% and inductive drop of 4%. Find loading of on each transformer. So what is given? Ohmic drop and inductive drop, that is nothing but impedance is given in percentage impedance, that means per unit system. So we can write impedance ZA is given. Transformer A ohmic impedance is 3 plus J5, right? It is given in percentage, and ZB is given as 2 plus J4, but they are at their base value. So base value for this is 750 kVA and for this it is 500 kVA. So we need to find first these impedances on common base value. So I can take any one as common base value. So let me take 750 kVA as base value. Then impedance ZA will remain as it is, whereas ZB will be calculated on the basis of this base value. So say base value is 750 kVA. Therefore I can write here ZB, that is impedance of second transformer, will be calculated on the basis of 750 kVA. Its capacity was 500, so it will be 2 plus J5, and if I calculate it, it will come as 3 plus J6. So now this impedance is available at same base. We know load shared S1 and S2 in terms of impedances and load impedance. So let me find first ZA plus ZB, or we can use directly. ZA plus ZB is required, and load impedance is, so load to be shared is 1000 kVA and at power factor of 0.8 lagging, that means minus 36.87, right, kVA. Now I can find SA, load shared by transformer A, that will be SL, impedance of second transformer by total impedance. So I can write here 1000 at an angle of minus 36.87. ZB is 3 plus J6 divided by ZA plus ZB, right? So ZA is 3 plus J5 plus ZB, we calculated 3 plus J6, and it will be 3 plus 6i divided by 6 plus 11J. So it comes as, in terms of polar form, 535.37 at an angle of minus 34.82 kVA. So we got load shared by transformer A will be 535 kVA and operating power factor will be cos of 34.82, that will be lagging. right? And load shared by transformer B will be total load minus load shared by A, SL minus SB. We can calculate by this formula also. We will put SB equal to SL ZA by ZA plus ZB. So this is what 1036.87 minus 535.37 at an angle of minus 34.82. So if you do calculation, it will come as 36.87 minus 535.37 at an angle of minus 34.82. It comes as, in polar form I will write it, 465 kVA at an angle of 39.22 minus 39.22 kVA. So we got this value. Load shared will be like this. In kVA you can calculate in kilowatt also. If I multiply kVA with power factor, I will get kilowatt. So this is what numerical on parallel operation at common base, right? Now numerical on three-phase transformer. So say for these two connections we need to find. So one transformer is given, three-phase stable transformer is connected to 6600 volt mains and takes 10 ampere. So line voltage and line current is given. Find secondary line voltage, line current, output for following connection. If N1 by N2 equal to 12 is given, right? For delta delta and delta star connection they are asking. N1 by N2 is, if I want to write K transformation ratio, that will be N2 by N1 and that will be 1 by 12. So for delta delta connection we know, if I have delta here, for delta delta, line voltage is 6600 volt and phase voltage will also be 66. Line current is 10 ampere and phase current will be 10 by root 3 ampere, and voltage here will be same 6600 volt. When it is transferred here, so secondary voltage is K times primary voltage. So voltage here will be K is 1 by 12. So 1 by 12 into 6600, that is nothing but 550 volt. So that will be voltage across phase and same voltage will appear across line also, right? And this phase current 10 by root 3 will be transferred here. I2 will be I1 by K, so that will be 10 by root 3 divided by K. So it will be multiplied by 12. 1 divided by K means divided by 1 by 12, that is nothing but 12. And current here will be root 3 times of this current. So 10 by root 3 into 12 into root 3, it comes as 120 ampere. So we got line current, line voltage. For this line current is 120 ampere and line voltage is 550 volt. Output, if I want to write, so S will be root 3 VL IL. S is complex power or kVA rating. So root 3 into 120 into 550. So it will come in VA, or I can write in kVA. 120 into 550 root 3 divided by 10 power 3. So it will be 114.3 kVA, right? So this is what line current, line voltage and kVA for delta delta connection. Let us see for star star connection what will be scenario. So I have star here, sorry, for delta star connection. So I have delta connection here and I will have a star connection. right? So voltage, line voltage 6600 volt, and here also voltage will be same, that will be 6600 volt. Line current is 10 ampere and phase current will be 10 by root 3 ampere. So this voltage will be transferred with k times. I can write here, so phase voltage, that will be 6600 volt into k, that will be 1 by 12, so it is what, 550 volt. So this is what phase voltage, and line voltage will be 550 root 3. Okay, now this phase current will be transferred here, so I am showing here. So 10 by root 3, I2 will be I1 by k, so 1 by 12, that is nothing but 120 by root 3. So same current will flow in line also. So line current is 120 by root 3 ampere, and line voltage we got as 550 root 3 volt. As output, if I have to write, that is root 3 VL. VL is 550 root 3 into IL 120 by root 3. So it comes as same value, root 3 cancel, and it will be same, root 3 120 into 550, so it will be 114.3 kVA, right? So this is what we are seeing. The values, the output is remaining same, but line voltage and currents are changing if connections are changed. Now let me solve one more numerical. Suppose question 3 say, I have a connection given, numerical, A terminal, B terminal, C terminal, there is one switch. Okay, it is S1, and there is one more switch, S2. It is connected like this. These are connected here, and it is connected like this. And I have secondary side as the star connection. So say this is A terminal, this is B terminal, and this is C terminal, and they are connected like this. Right. Now what is question? That in delta star connected three-phase transformer, is used to step down, voltage from 11,000 volt to 415 volt line to line. line to line. It has two switches. It has two switches, S1 and S2. Under normal condition, in normal condition, S1 is closed and S2 is open. S1 is closed and S2 open. In certain condition, if S2 is closed and S1 is open, then in this case find voltage across LV terminals of A and C. So they are asking, when S2 is closed, S1 is open, what will be voltage across A and C? This is LV and this is HV, right? So very first thing, I have delta and star connection. It is HV, it is LV, and 11,000 volt is there, that is line to line, and here it is 415 volt. So if I have to find transformation ratio K, so K will be phase voltage of secondary side divided by phase voltage of primary side. So K is, say, V phase of LV side by V phase of HV side. Now secondary is star and line voltage is given, so phase voltage will be 415 by root 3, and HV side is delta, so phase voltage and line voltage will be same, so it will be 11,000, right? So this is what transformation ratio. We will have number of MCQs based on this also. Now I can relate it. Let me draw in phase sequence A, B, C, and I have star. Same circuit A, B, and C. So say this voltage is VAB, VBC and VCA, right? It is VAB, VBC and VCA. So voltage here, phase voltage I will take as VA, phase voltage here I will take as VB, and phase voltage here I am taking as VC. So I can show that this phase voltage by this phase voltage will be transformation ratio. So I can write as VA by VAB equal to VB by VBC equal to VC by VCA. That is nothing but K, right? And in delta, by KVL we can write VAB plus VBC plus VCA equal to 0. We know when S2 is closed, B and C are shorted. You can see B and C will be shorted when S2 is closed. Therefore, voltage between them will be 0, but they will be at same potential. B terminal and C terminal will be at same potential, so VBC will be 0. So I can write here from this VAB plus 0 plus VCA equal to 0, or VCA equal to minus VAB. So what we got? See, voltage across this is in antiphase with this one. So I can write, if VAB is reference voltage, if VAB is 11,000 at an angle of 0, right? VAB, that is voltage of delta side. So VCA can be written as minus 11,000 at an angle of 0, or I can write as 11,000 at an angle of 180 volt. So this is what, both voltages are in antiphase, right? Now if I have to find voltage between this VAC, which they are asking, it will be what? VA minus VC. I can put VA and VC in terms of K. VAB, VBC, VCA, they are known to us, right? VAB is given, that is 11,000 at an angle of 0, VBC is 0, and VCA just now we calculated. So I can write in terms of this, what is VA? VA is K times VAB, K VAB, minus what is VC? K times VCA. So if you put values here, what is K? K is 415 by root 3 into 11,000. VAB is 11,000 at an angle of 0, minus VCA is this value, 11,000 at an angle of 180. So if you do calculation here, it will be 415 divided by root 3 into 11,000 into 11,000 minus 11,000 at an angle of 180. So it comes as 479.2 volt. So VAC, what we got? VAC will be 479.2 volt. That's all for the numerical on these three-phase circuits.